In this section, we discuss benchmarking of AutoML systems. Everything we have covered so far, evaluation protocols, statistical tests, nested evaluation, and anytime performance plots, has been building towards this. Benchmarking is where we attempt to draw general conclusions about which systems work well, under what conditions, and why. It is also where the accumulated methodological depth of cutting corners becomes most visible. So, let us start with what a benchmark actually is. Benchmarking is the systematic comparison of methods across a defined set of tasks. The goal is to draw conclusions about relative performance differences that are more general than what any single dataset comparison could support. When we evaluate two AutoML systems on one dataset, we learn something about their behavior on that specific problem. However, when we evaluate them across a diverse collection of tasks, we can begin to make broader claims about which system is preferable and under what conditions. A benchmark has three essential components. The task suite is the collection of the datasets or problem instances on which systems are evaluated. The protocol is the fixed evaluation procedure, the time budgets, hardware specifications, train task splits, and everything else that determines how systems are run and compared. And the performance measure is the metric used to score systems on each task. All three components matter equally. A benchmark with a well-chosen task suite but an inconsistent protocol produces irreproducible results. A benchmark with a rigorous protocol but a poorly chosen task suite produces results that do not generalize. And the benchmark with the wrong performance measure may reward behavior that is not actually desirable in practice. Good benchmarks are reproducible, fair, and representative of real-world use. And achieving all three simultaneously requires careful design. Before discussing what makes a good benchmark, it is worth grounding the discussion in a theoretical result that has direct practical consequences. The so-called no free lunch theorem states that no algorithm dominates all others across all possible tasks. More precisely, if you average the performance of any two algorithms across all possible problem instances, they perform equally. This is a theoretical result with idealized assumptions, but its practical implication is important and robust. The outcome of any comparison between methods depends on which tasks you choose to include. There is no algorithm that is universally best, and therefore no benchmark that is universally valid. This has a direct consequence for how we interpret benchmark results. A benchmark implicitly defines a distribution over tasks. The conclusions we draw from it only generalize to tasks that are drawn from the similar distribution. A system that performs well on the tasks in a benchmark X may perform poorly on tasks in a benchmark Y if the two task suites represent different problem distributions. The most dangerous manifestation of this in practice is cherry picking. Selecting datasets that happen to favor one's own method or system while excluding datasets on which it performs poorly. Cherry picking is sometimes intentional, but more often it is subtle. Researchers naturally gravitate toward datasets where their systems look good and may genuinely not realize they are excluding unfavorable cases. A credible benchmark must actively resist this by covering a diverse range of tasks. Varying dataset sizes, different feature types, different degrees of class imbalance, and different levels of intrinsic difficulty. Diversity is not just a desideratum, it is the mechanism by which a benchmark results earn the right to be called general. Let us briefly survey the main benchmark resources available in the AutoML community so you know where to look when you need to evaluate or compare systems. OpenML CC18 is a curated collection of 72 classification datasets from the OpenML platform. It has become a widely used default task suite for comparing AutoML systems on tabular classification, and you will encounter it frequently in the literature. The AutoML benchmark is a standardized framework specifically designed for comparing AutoML systems. It provides controlled resource allocation, reproducible data splits, and supporting for running multiple systems under identical conditions. HPOBench and HPOB are focused benchmarks for hyperparameter optimization. Rather than running the full ML pipeline, they provide surrogate evaluations or lookup tables, pre-computed performance values for a large number of configurations, which makes them computationally cheap and useful for developing and testing HPO algorithms without incurring the cost of real model training. YapoGym is a surrogate benchmark suite that covers a large number of HPO scenarios efficiently. It combines the diversity of many real-world tasks with the low evaluation cost of surrogate models. PD1 focuses specifically on hyperparameter optimization for modern deep learning architectures, including ResNets and transformers. This is an important addition to the benchmark landscape as deep learning has become a central application domain for AutoML. Finally, CARPS is a recent unified benchmarking framework that integrates HPOBench, YapoGym, PD1 and others into a single interface, making it easier to run consistent comparisons across a wide range of HPO scenarios. Once we have run all systems on all tasks in the benchmark, we face an aggregation problem. Raw performance scores are not directly comparable across datasets. Accuracy on one dataset, AUC on another, mean squared error on a third, and even within the same metric, the scale and range can differ substantially between tasks. We need to normalize before we can aggregate. Two normalization strategies are commonly used. The first is rank-based aggregation. For each dataset, we rank all systems by their performance and then average ranks across datasets. This is robust to differences in scale and outliers, and it directly captures the ordinal relationship between the systems. The disadvantage is that it loses magnitude information. A system that barely beats another one on one dataset is treated the same as one that dominates it entirely. The second strategy is normalized scores. For each dataset, we scale performance relative to a baseline and a reference ceiling, so that 0 corresponds to the baseline and 1 corresponds to the best possible performance. This preserves some magnitude information but requires choosing the baseline and ceiling carefully. After normalization, we apply exactly the statistical testing workflow from the statistical test section of this chapter. We begin with a Friedman omnibus test to check whether any differences exist across all systems simultaneously. If it rejects the null hypothesis, we proceed to post-hoc pairwise comparisons with appropriate multiple testing correction, Holm or Nemeny. The results are then visualized using critical difference diagrams, which show the mean ranks of all systems and indicate which pairs are significantly different. This workflow ensures that the conclusions we draw from the benchmark are statistically grounded rather than based on informal inspection of tables and figures. Even a carefully designed benchmark can produce misleading conclusions if certain threats to validity are not addressed. Let me go through the most important ones. Time budget sensitivity is particularly relevant for AutoML systems. As we discussed in the plotting section, rankings between systems can change substantially as the budget varies. A system that is best at 10 minutes may not be best at 1 hour. Reporting results at a single fixed budget without examining any time curves can therefore lead to conclusions that are specific to that budget and do not generalize. The remedy is to report results at multiple budgets or better as full anytime performance curves. Hardware heterogeneity is a practical but serious concern. Wall clock time depends on the hardware on which a system is run. CPU speed, memory bandwidth, parallelism. A system that makes heavy use of parallelism will benefit disproportionately from a many-core machine. If systems in the same benchmark were run on different hardware, the time budgets are not comparable and the results cannot be fairly interpreted. Hardware must be documented carefully and all systems should be run on identical infrastructure. Dataset leakage is a subtle but important threat. Public datasets are visible to everyone, including the developers of the systems being benchmarked. A system whose hyperparameters or architecture were tuned using datasets that appear in the benchmark has an unfair advantage. It has effectively been trained on the test distribution. This is difficult to detect and almost impossible to fully prevent, but it is worth being aware of when interpreting results on widely used benchmark suites. In particular, in the age of large language models, this is also in general machine learning research a serious concern. Metric choice can change conclusions, And a system optimized to minimize classification error may rank differently when evaluated on AUC, log loss, or F1 score. The choice of metric encodes assumptions about what matters in the application, and different choices can favor different systems. Always be explicit about why a particular metric was chosen. Finally, stochasticity. A single run per system per dataset is insufficient. As we have established throughout this chapter, performance estimates are random variables and single run comparisons cannot be trusted. Always use multiple runs, report uncertainty, and apply statistical tests. Let us close this video with the key takeaways from this section and from the chapter as a whole. A benchmark is only as credible as the quality of its three components: the task suite, the protocol, and its openness to scrutiny. Weaknesses in any one of these undermine the conclusions drawn from all the others. Cherry-picking datasets is the most common and most serious threat to the validity of benchmark comparisons. The no free lunch theorem tells us that no system dominates across all tasks, which means the choice of task suite determines the outcome. Diversity is the safeguard here. Fair benchmarking requires controlled resources, nested evaluation, and multiple runs with reported uncertainty. Each of these requirements corresponds directly to a section of this chapter. There are not additional bureaucratic constraints, they are the practical instantiation of the methodological principles we have developed throughout. Raw scores must be normalized before aggregation, and the aggregated results must be subjected to the statistical testing workflow. Friedman first as an omnibus test, post-hoc pairwise comparisons with correction second, and critical difference diagrams for visualization. And finally, benchmark results are always relative to a specific task distribution, a specific time budget, and a specific hardware environment. Generalizing beyond those conditions requires caution, explicit justification, and ideally additional experiments on a broader task suite.